Hello everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber. Talk about statistical tests again, and we're going to talk about Spearman correlation. We're going to go very easy given the time of the day. Not going to talk about anything particularly crazy, and we are going to go through a little bit of gossip about Spearman, the guy we're going to talk about today, and Carl Pearson, the guy we talked about on our last teaching session. So usual disclaimers, I'm not a statistician or an expert in statistical softwares, but I like to kind of play with both. A quick summary of what we talked about. We talked about probably the most important thing in the world, which is assumptions, particularly normality and scholasticity. And then we touched base about others, just sphericity, etc., etc. But these are the two really that you need you guys to remember. We talked about students T, ANOVA, Wedge ANOVA, two-way ANOVA, pair sample t-tests, repeated observations ANOVA, and Pearson's correlation, and how to run them. So today we're going to continue our journeys through the analysis of continuous data. And in this particular case, we are going to move towards skewed data. And we will see in what context particularly. We're going to run some examples with Genovi. So, Spearman. Spearman was, well, obviously, as you can guess, a gifted statistician, but he was also a very well-known psychologist. And the vast majority of his fame comes from his theory on general intelligence, published back in 1904. This kind of laid the base for what is the modern interpretation of intelligence in humans, and has then sort of laid the ground to a massive amount of work that has been done in cognitive psychology following this publication. He worked at UCL, and as you recall, also Carl Pearson worked at UCL. The two had a fairly troubled relationship across time. When Charles Spearman came on to UCL, Carl Pearson was already a very well-established academic. He had already done loads of research for about 6-7 years into his senior career. It was pretty much academically impeachable, as described in a number of papers out there. So we'll start looking very quickly at the work of Carl Pearson again, and then we'll look at why Spearman managed to upset him. So we talked last time about the concept of correlation. So basically, the measure of statistical relationship between two variables. And we talked about how this can be mathematically measured by dividing the covariance of the two variables for the product of their standard deviations. That's all well and dandy, and in all honesty, relatively unimportant, because any piece of statistical software can do that for you nowadays, as we will see later on. But it is important to remember that there are some relevant pieces of information in this slide that has to do with the way the numbers are crunched, covariance and standard deviations. So we're talking about measures of spread of data, basically, that derive fundamentally from the concept that the data is normally distributed, and that's where Carl Pearson's work really functions well. As I said, all of this works if the data is normally distributed. So what do you do if it isn't? And what if extreme values are present? Now, this is not uncommon. It is very uncommon. It is very common. And in this case, Pearson correlation becomes fairly unreliable. So basically, when you look at your data and you start, glancing at some charts, you very quickly realize that instead of looking nicely normally distributed without outliers, it actually looks like this. And this is data from my dissertation. And as you can see here, there are some very significant outliers. And when you try and run a correlation matrix between likes and, for example, citations of a paper, likes on the Twitter network, I mean, and time cited following the publication of the paper on other journals, you realize that your scatter plot just looks awkward. And that's probably because there are a lot of outline variables, outline numbers in there. So Spearman said, well, actually, I have an idea that might fix this problem. And he published a number of papers on it, particularly the one that you can see on top of his portrait, saying that, well, he could fix the problem that Carl Pearson couldn't fix. And obviously, Carl Pearson wasn't particularly impressed with that. So he did publish a few papers in response to that. Allegedly, their working relationship in UCL was much more troubled than the papers would portray. But the papers themselves, you can see they're referring to each other in terms that are not exactly academically polite, I would guess. So what was the idea that Spearman had? Well, instead of using the absolute number that you've got in front of you, why don't you use a rank? What does that mean? Well, you remember a few sessions ago, we were chatting about an imaginary group of people growing marijuana plants and trying to figure out what worked and didn't work in terms of getting good results with grams. So if you imagine for a second that you've got 4 plants of marijuana here on the table on the left, right? You want to see if the plant height correlates with the grams that you get out of a plant. And as you can see, there are some plants that are fairly, I don't really know how tall a marijuana plant is, actually. I think it's much taller than that, but it doesn't matter. You've got some plants here that are fairly homogeneous, so 25, 23, 27 centimeters, then a crazy tall plant. And you can see that they produce 3, 5, 4, and 6 grams each. When you have a value like this, your correlation matrix will be fairly upset by it. And if you try and plot this on a chart, you will immediately realize that this is an outlier. So instead of using the absolute value, you rank your plant height by first, second, third, and fourth. So plant number 1 will rank number 2 because it's 25 centimeter. Plant number 2 will rank 1 because it's 23 centimeters. It's the lowest value, and so on. And then you rank the grams equally. And this is what ranking means. And then you can see that rank number 2 corresponds to rank number 1, rank number 1 to number 3, and so on. That does have quite a significant impact in the way correlations calculation work, because it does reduce the effect of outliers. So if you look at this chart here on the left, there's obviously a bunch of points, and they seem to correlate towards a relatively well-established positive correlation, but there are also some outliers. If you run a Spearman correlation on this, you get a fairly high correlation coefficient, which is lower if you run it as a Pearson. That is to say, these outliers are affecting the correlation less if you run Spearman versus Pearson. It also seems to be more reliable in nonlinear relationships or small samples. So if you look at this relationship, it's clearly not a straight line, is it? However, Spearman correlations still suggest that there is a very, very strong correlation, while Pearson correlation is slightly lower in terms of the mathematical value. However, you can also see that if there isn't a correlation, they both pretty much perform at the same level, which is again a sign of Spearman's reliability has been slightly superior to Pearson in probably most environments. So it's just less sensitive to crazy values that can lie around in your data set. The interpretation of the result remains the same. So, 1 is a pretty much perfect positive, 0.9 strong positive, 0.5 weak positive, and so on. So you interpret the result in the same way, but the result you get can be slightly different depending on how your points lay on your chart. a final point, I've explained this picture last time. Correlation and causation are not the same thing. You can look this up if you search Pastafarianism online. It has to do with a, let's call it a pretend religion, a satirical religion. And one of the things that are often talked about in relationship to this religion is the strong belief that the average temperature of our planet are going up, not because of what we are doing to the planet, but because the number of pirates have been declining. And this is clearly a joke and is meant to say that, again, correlation is not the same thing as causation, if that makes sense. Look it up, it's very funny. So let's go on with a practical example. For my dissertation, as you probably by now know by heart, because I've spoken about this many times, I collected data about papers that were advertised on Twitter by publishing journals. For the purposes of today's example, we're going to check if the likes data are correlated with citation data. In this particular piece of software, which is called Jamovi, as we said many times, you'll find correlation matrices under regression. We said we were going to look at time cited, and we were going to look at likes. Is that right? Yes, that's what we said we would do. So we've got a few options here. What should I do before deciding whether I'm going to run a Pearson or a Spearman correlation? Let's see who's online. Pratik, do you want to have a go? What's the first thing I should check?
Should we check for skedasticity?
Even before that?
Normality?
Normality, absolutely. So for a normal distribution, I can use Carl Pearson work. For a non-normal distribution, I should use a Charles Spearman work. So I'll show you the results of both. As you can see, in both cases, you do get a statistically significant correlation between the two. However, the Pearson's correlation coefficient is 0.339, while the Spearman's correlation coefficient is higher. And you can also get your correlation matrices here. So you can actually do your depiction, if you like, for your papers or whatever. To check which one I should have used, I should go on descriptives, and I should put there likes and time cited, and then I should look at some statistics, including a Safir-Wilk test, which, as you can see, is statistically significant. As a result, this data is not normally distributed. Well, this is the result of the fact that the data is not normally distributed. If you want, you can also look at some plots, which will also show you the same. So you can see the massive amount of outliers we've got here, if that makes sense. You do bar plots, histogram, density plots, whatever you like. It's quite versatile piece of software. Okay. Perfect. So to recap, regression, correlation matrix, put whatever you want to test there. We set that. And likes. Choose your one once you've tested for normality. And there you have it. You want to see your plot, correlation matrix. And it can also show you the statistics on the chart if you really want to. Okay, right, that it was the end of it. So I'm going to stop sharing. Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.